Hello everyone. In the previous lecture, I discussed about the production of radioisotopes by irradiating the targets with neutrons, and also we discussed how you can produce the carrier-free radioisotopes by different means. In this particular part, I will discuss the radioisotope production using charged particles, and also some of the other aspects of radioisotope production, like what are the ways how the radioisotopes are handled after irradiation, and particularly in Indian context, what are the mechanisms and processes by which the radioisotopes are produced and supplied to the users. So in the charged particle irradiation, you can use a cyclotron or a linear accelerator or a tandem accelerator. Tandem means two-stage accelerator. And then, depending upon the irradiation time, the facility that is available to you, you can get the radioisotopes. You need the suitable beam and the target. So the knowledge of nuclear reaction will be very much useful in choosing what beam, what target. So if you have a cyclotron and it is giving proton beam, then you already have the projectile fixed. So now you can fix a target and accordingly go for radioisotope production. Before you go for the radioisotope production, you need to know the excitation function. That means the cross section. So this is the cross section, sigma r versus energy of the projectile. Then this is the total cross section, and you will have the excitation functions of different products like alpha n, alpha 2n, alpha 3n, and so. So depending upon the excitation function for a particular radioisotope, so you have to choose the energy of the projectile and also make sure that this is available from the machine that you are going to use. So these aspects we have already discussed in the previous lectures on nuclear reaction. Now we come to see what are the isotopes that can be produced using proton, deuteron, and alpha particles. The heavy ions, as projectiles can be used for radioisotope production, but you will find that the heavy ions are having multiple charges. So the currents are low, and you may produce many other isotopes which may not be useful. So mostly for commercial applications or applications in industry or healthcare, whatever radioisotopes are produced, they are either produced using protons or alpha particles, or deuterium, using cyclotrons, because cyclotrons give rise to very high beam intensities. Beam intensity means current in microamperes. So 1 microampere of proton will have 6.24 10 power 12 particles per second. Accordingly, 1 microampere of 1 microampere of alpha particles, suppose the alpha particle 1 microampere current it will have. This is a 2 plus charge state, 6.24 upon 2. That is how typical currents, some of the accelerators produce milliamp currents. Like for medical cyclotrons, you want very high activity of a short-lived isotope, you go for milliamp current. 1 milliamp, 10 power 15 alpha particles or protons per second. That is the kind of intensities you use. So proton-induced reactions are used to produce fluorine 18. You can produce cadmium, indium 111, and F18 is used in PET, the positron emission tomography. So this F18 is having only 109 minutes half-life, so about 2 hours, and so you irradiate H2O18, H2O18, and PN to 18F, and you have to do very quick chemistry because the half-life is only 109 minutes. And you tag a glucose molecule, fluorodeoxyglucose, and the tag is F18, and then you can transport it to hospital for PET operations. This 111 also is used in the analysis, the diagnosis of diseases. The 111 indium emits beautiful gamma lines in 100 to 200 kV range. So it is also used in genetics. Again, another isotopes, gallium 69 PN reaction, P2N is germanium 68. The germanium 68 has a half-life of 270 days, which decays to gallium 68, which is a beta plus emitter, and hence it's a PET radioisotope. any beta plus emitter being short-lived are ideal for PET diagnosis, positron emission tomography. So you can have a generator system, germanium, gallium generator system. So because you have to supply this gallium-68 to the hospitals. So in the hospital, you can have a germanium-68 column and go on milking every few hours gallium-68. Similarly, thallium-201 is used in stress test, single photon emission computed tomography. Irradiate thallium-201. This is actually thallium-203, not 1. P3N, lead-201, and which is emitting beta plus or electron capture, give rise to thallium-201. And this having half-life of few days, you can use it for spectral analysis. Camera, scintigraphy camera. 125 iodine 60 days is another isotope of iodine used in, emits a low energy gamma ray, and it is used in radio immunoassay of iodine, like thyroid hormones. So iodine 127 P3N, xenon 125, and 127 iodine. You can also produce by 127 iodine target P5N, xenon 133, going to 123 iodine. So some of the isotopes of iodine 123, 125, apart from 131. 131 is a beta emitter, and these are emitting electron capture and the X-rays and low energy gamma ray. So depending upon the type of application you have, you can choose which isotope of iodine is suitable. Deuterium targets are used to produce sodium-22 and oxygen-15. Sodium-22 is a positron emitter, though it is not used in PET because it has got a half-life of about a year or two. So, but it is a source for calibration. So it emits 511 keV gamma rays. If you want to calibrate your system and you can study chemistry of positronium, so positron is a positron source, and many chemistry of positronium atoms are done with sodium-22. In fact, there are positron beams. You can take a source of sodium-22 which is emitting positron, and you can accelerate these positrons to use for many applications. Oxygen-15 is a beta emitter, and you can use this for the PET analysis, a short-lived isotope produced by nitrogen-14 DN reaction. For alpha-induced reaction, again 111 indium, technetium-95, plutonium-238. 238 plutonium is a heat source for the space applications. In satellites, you can want to produce some power. See, typically, 1 watt of, if you want to have 1 watt heat, then about 2 grams or 1 gram of plutonium-238 gives some 2 watts. So typically, that is the kind of wattage you can get from plutonium as a heat source. So these are the isotopes that are produced using cyclotrons. There will be many. I'm just giving you examples. There are more isotopes. In fact, we will come along them and discuss further. So many radioisotopes which are not produced in reactors, and many isotopes which have different types of applications where you require carrier free. It may not be possible by reactor, so you go for axial approach. So this is the list of cyclotron produced radioisotopes: sodium-22, magnesium-24 D alpha, cobalt-57, nickel-58 P2N, gallium-68. You can directly produce gallium-68, or you can go for gallium-69 P2N reaction, indium-111, cadmium-112 P2N, iodine-123, tellurium or xenon as a target material, thallium-201, thallium-203 P3N, lead-201 followed by electron capture decay, carbon-11, nitrogen-13 and oxygen-15. These are all positron emitters, short-lived ones. You can see 20 minutes, 9 minutes and 122 seconds and 109 minutes. They are all positron emitters. Some of these isotopes are actually, the cyclotron is coupled to the PET facility directly because half-lives are very short. So these are the reactions used for producing these alpha positron emitters, and they are widely used in PET telepharmacy. Palladium 103, 16 days. Again, rhodium 103 P2P reaction. So you will find, there are hundreds of radioisotopes having different applications. So what we can do, you can just suppose you want tracer of a particular element. You want to trace the path of an element, take the nuclear chart, look for the isotope having suitable half-life, decay characteristics, and then see in what way you can produce a particular radioisotope. So having the knowledge of nuclear reactions, you should be in a position to find out a reaction which will give you the desired isotope, proper yield, particular activity, and whatever activity you need, and particular chemical form also. You should be able to do the chemistry and deliver it to the users. So let us compare the radioisotope production in a reactor and a cyclotron with different attributes. You can see here, in the case of a reactor is a big sea of neutrons. So you can irradiate large amount of target material, like cobalt metal, you can irradiate 10-20 grams, even 100 grams you can irradiate. But in a cyclotron, where the beam is traveling, first of all, the beam dimensions are very small, few millimeters. So you cannot irradiate large quantity. Even if you irradiate larger pile, it will not bombard that material. Only a very small section, cross section, the target will be irradiated. So small amount of target only can be irradiated in the cyclotron. So cyclotron, I am saying, is representative of an accelerator, but most of the time you will find the radioisotope production by charged particles is mostly done in cyclotrons. So I'm just comparing reactor and cyclotron, but this is also valid for any charged particle accelerator. Accordingly, the specific activity is generally low in reactor neutron irradiation, particularly when the target material is irradiated and become by N-gamma reaction, you get the isotope of the same element. There have been cases like multiple neutron capture or like this one, beta decay, then N-gamma followed by beta minus decay, then you can get carrier free. But in general, if you irradiate a target material by N-gamma, you will get low specific activity. In cyclotron, you are using a charged particle, so you are changing the atomic number of the radioisotope compared to target, and therefore you have very high specific activity of the produced radioisotopes. Number of targets at a time in a reactor, you can irradiate large number of radioisotopes in the target materials. So at a time, many targets are being irradiated, and you can just remove which one you want to remove depending upon the time of irradiation and their half-lives. You can irradiate many targets in the reactor. So throughput is very high, but in a cyclotron, at a time, only one target. We suppose you have multiple beam lines. At a time, the beam will go in a particular beam line. So there is no point putting irradiation in other beam lines at that point of time. At a time, only one target irradiation. Irradiation time can be kept long. Like I was telling, cobalt, you irradiate for years together. Half-life is 5.27 years, so you can irradiate for 1 year. In the case of accelerators, you cannot create irradiate. You cannot hold the accelerator for one target production exclusively. So usually the irradiation time will be 1 day or few hours and so on. And the beam time is very costly. Cyclotron operations are very costly. Type of decay of radioisotopes produced in reactors, mostly beta minus, but in the case of cyclotron produced radioisotopes, beta plus electron. So they are neutron rich, they are neutron deficient. That is the only difference. And the cost of production accordingly, in the reactor, cost of production is low, but in the accelerator, production is very high. So you have to weigh, you have to optimize the cost also, but when you are delivering to for industry, some applications, or in hospitals, so that you produced, whatever the cost that will go into the final cost of the particular operation or test. All these factors are important to choose what is the method of. So you may get a low specific activity in the reactor, but it is cheaper. You want to go for high specific activity in cyclotron, you have to pay for it. That is how you have to assess the situation and plan. Now, many times, there are many elements have multiple isotopes, and you want to produce a particular isotope by N-gamma or charged particle, but there will be side reactions. Other isotopes also will interfere. They will produce other activity which may not be required. And so at that point of time, you need to have enriched isotopes. So if an element have got multiple isotopes, and you want to irradiate a particular isotope, you need to get rid of the other which are not useful. So enriched isotopes are required And the isotope enrichment is a very expensive process, so that adds the cost to the whole production of the radioisotopes. They are expensive, but at many times they are inevitable. You cannot afford to not have the enriched targets. So I am just giving you some examples. What are the situations in which you need the enriched targets? So there are situations where you want the radioisotope with high yield and high specific activity. For the target atom should contain only radioactive elements. That time you cannot have the other isotopes. You see, just to give an example, 112 India tin N gamma 113 tin. So you want 113 tin, which is used in medicine. Now the abundance of 112 tin is only 1%. You can see here other isotopes of tin will also capture neutron, or the volume, say 99% of the tin is other isotopes. So if you produce 113 tin, bulk of the tin is still the natural tin, and so the activity produced of 113 will be very small because 112 is only 1%. So what you do, you try to enrich 112 in the sample so that your specific activity will go up and your yield also will go up. Similarly, fluorine 18 that you want to produce for PET operations, oxygen 18 is very small percentage, 0.2%. Bulk of the oxygen is oxygen 16. So if you irradiate natural water, you will get very small activity of F18 because oxygen 18 is very small abundance. So what you do, irradiate, you enrich water in, so you have H2O18. And you can irradiate, you can enrich oxygen 18 up to more than 95%. See, these are low mass numbers, so it is easy to enrich the low mass elements. So these are the things, you necessarily need to enrich the target element in the desired isotope. Second requirement is to minimize contamination from unwanted reactions. You are looking for a particular isotope, but there are other target isotopes which may give you unwanted activity which is not desired. For example, 187 N gamma gives 188 rhenium. We want 188 rhenium for our application, but there is another reaction, 185 rhenium N gamma, 186 rhenium, which is not required. So you have one isotope 3 days, other isotope 17 hours. And abundance of 185 is 37%. 187 is 62%. So these are the two reactions concurrently happening. Your isotope of interest is actually 188 rhenium, which is used in therapeutic applications. So you have to, to obtain pure rhenium 188, you have to allow rhenium 186 to decay. But how you can allow it to decay? Rhenium 188 is short-lived than 186 rhenium. So it is not possible to allow 186 rhenium to decay. Therefore, what you do, you use enriched 187 rhenium. That is what I was telling, that tungsten 188, if you have, you can produce by 2 neutron capture, that will give you 188 rhenium. And so these problems are not there. So by N gamma route, if you produce 188 rhenium, it will be contaminated with 186, which is longer lived than 188. So those situations you require necessarily enriched isotope. Similarly, again here also it is similar to that. Radionuclidic purity means the sample should be pure with regard to particular radioisotope, and there can be parallel reactions. For example, you want to get 123 iodine, you irradiate xenon 124 P2N, cesium 123 going to xenon 123, and then by electron capture it goes to iodine 123. But the abundance of xenon 124 is only 0.095%. So if you irradiate natural xenon, it has got very low abundance, and so you get very small activity. 126 xenon also has got about same abundance as 124 xenon, and that also gives you by similar reaction 126 xenon P2N reaction, 125 cesium, electron capture 125, and so this is actually 60 days. So 125 iodine is longer lived than 123 iodine, and so it will always contaminate your spectrum. So if you have 123 iodine produced by xenon 124p2N reaction, you will invariably have 125 iodine, which is longer lived. And therefore, there will be always contamination. Therefore, you need to enrich xenon 124 up to more than 99%. The gaseous isotopes are easy to enrich. Different methods are there available for isotope enrichment. And so the enrichment of isotopes is a very common technology these days, and many vendors are available to supply you enriched targets. There are situations where the target element may contain isotopes which have very high neutron absorption coefficient. So you want to produce one isotope of that element, but the other isotopes may have very high neutron absorption cross section. So they will suppress the neutron flux in the position. So they act as neutron poisons. Means though the isotopes which have very high cross section for neutron capture, they act as neutron poison. They will actually absorb the neutrons and reduce the flux. For example, you want 153 samarium for many medical applications. You irradiate 152 samarium N gamma and you get 153 samarium. Half-life is about 46 hours. But if you see here, you have 149 samarium N gamma, 150 samarium. Though 150 samarium is stable, it will not give you any activity. But the very high cross section, 41,000 bond of samarium 149 N gamma, this high cross section will reduce the neutron flux. Most of the neutrons will be captured by 149 samarium, and so it's like a neutron poison. So it will affect the neutron economy in that position, and your yield of 153 samarium will be less. So these are the reasons where you need to have enriched isotopes. There are other ways also where you can have radioisotopes. I have separated this class of radioisotope because they are very handy in many applications. So I give you some of the generators. Radioisotope generators means you have a parent-daughter relationship. You have a long-lived parent and short-lived daughter, and you can put in a column or a A is here, and you can milk B. So this is cow. It's called cow. You milk the cow. So you can hold the parent isotope in the column, and you can go on milking. As I discussed in the molybdenum-99 case, you can milk technetium from molybdenum generator. They are called radioisotope generators, and they are very popular these days because you can send the people who are manufacturing these generators. They can sell the generators to the hospitals, and hospitals have their own hospital radiopharmacy. They can go on milking the isotope of interest. So molybdenum-99 is the parent of technetium-99M. Technetium-99M is the workhorse of nuclear medicine, particularly for the diagnostic radiopharmacy. So SPECT, single photon emission computed tomography, you are doing the image of an organ. You inject a labeled compound labeled with technetium-99M, and then when it is going in the bloodstream, a particular organ where the blood is flowing, you can take the image of, like for example, heart imaging. You can see what part of the heart is, if there had been a heart attack, then what part of the heart is infructuous. You can see in this one. So 66 hours and 6 hours is ideal transient equilibrium. You can go on milking technetium from that. Another pair is germanium-68, gallium-68. It's a beta plus emitters. So for PET radiopharmaceuticals, you can use this generator, 270 days and 68 minutes. 113 tin and indium-113. Indium-113M is the radioisotope useful for diagnostic radiopharmaceuticals. And so you can milk it from 113 tin, having half-life 115 days, and this is 99 minutes. This internal transition, it emits more pure gamma emitter like technetium-99M. So they are ideal for imaging. Strontium-90, 28 years, yttrium-90, 64 hours. And so this is again another pair where yttrium-90 is used in therapeutic radiopharmaceuticals. Tungsten 188 decaying to rhenium 188, which is used in therapeutic radiopharmaceuticals. And cesium 137, barium 137 used in the laboratory experiments for the gamma ray half-life determination. And in many applications you will find 137 cesium is also used in blood irradiators. So these are another way of producing. Now I will just briefly discuss some of the activities in India. In India, we have at Trombay campus, we have the Cyrus reactor. That of course is not functioning now, but we have the Dhruva reactor, which is producing radioisotopes. And there is a sequence of events to irradiate in the reactor, take it to the radiochemical laboratory, and then process them, sent to other agency for distribution in the country. So inside the Dhruva, we have the reactor hall in Dhruva. Inside the reactor hall, these are the facilities for experiments, neutron scattering and other things. But inside the reactor, which is the calandria reactor, inside the reactor, you will have the positions where you can load the sample, irradiate them for a specific period of time, take out for processing. So these are from the irradiation. After the irradiation in the reactor, you bring them to the hot cells. Hot cells are, these are this you can see the yellow color in the windows. These are lead glasses because inside the hot cells, the radioisotopes of very large activity, curies, hundreds of curies are being handled, and the person who are handling them should not get the radiation dose. So the viewing window is not pure glass; it is made of lead glass. So lead will attenuate the gamma ray, so the personnel are not getting much gamma dose. So that is why you can see by lead, adding lead, some color will develop in the, and also the radiation, because of the radioisotope sources, they also have the tendency to generate colors in the glass materials. So the viewing window, and these are the master-slave manipulators. You can manipulate them and do the chemistry inside the hot cell. You have to open the can, do different chemistry, transfer from one port to other port. So all these operations are done in the sealed hot cells. This is a complete sequence of radioisotope production. You have the targets, you can have powder, you can put them in the tube, and then seal in these are the cans, aluminum cans. You fill the powder into this one, and then you can put a cap, you can do welding, irradiate in the reactor. This have to go quality check so that it does not leak. And then after this, you bring in the shielded casks from the reactor, stainless steel or pots, lead pots. They have to be transported to the processing laboratory where the people are now doing operations in the hot cell to separate the particular isotope of interest. They are then dispensed. You can bring it in the vials, properly capping them so that there is no leakage. There has to be a quality check. Many times the sterility also have to be checked if it is for direct injection to the human being. Then these are packed into the lead pots, and then we have the package. You have to give the proper package so that people can identify what is the dose, what is the activity and all that. And then they are supplied to the hospitals by the agency. For the charge particle irradiation in our country, we have a medical cyclotron facility at Variable Energy Cyclotron, Kolkata. It has been commissioned some time back. And this will give you proton beams of 30 MeV, and then you can produce these isotopes, which are positron emitters or electron capture emitting radioisotopes like gallium-67, helium-201, iodine-123, fluorine-80, gallium-68 by different types of reactions, P2N, P3N, PN, PN reactions. So I just discussed how they are produced in this discussion. And so like gallium-67 soft tissue tumor imaging, with helium-201 for myocardial perfusion imaging, after this test 123 iodine for thyroid imaging, F18 for glucose metabolism, and gallium-68 for PET analysis of neuroendocrine tumors. So these are the kind of activities are being produced at medical cyclotron. And in the country, there are several PET cyclotrons now available. Private hospitals have their PET cyclotrons, medical cyclotron PET isotopes, and particularly F18 is produced in these cyclotrons. You have the 16 MeV proton beam bombarding H2O18 that gives you F18, and then there is an automated radiochemical processing unit wherein within a few seconds or few minutes you will get the compound labeled with the fluorine 18. Then it can be directly sent to hospitals for PET imaging. So these are the kind of facilities that are available for. So in our country, the Board of Radiations and Isotope Technology, it's called BRIT, is the agency to supply different radioisotopes or different kits, and they also do the services for industry in medicine, medical industry, normal industry, and many other. Whoever wants radioisotope in the country, you will find radiopharmaceuticals, radioimmunoassay kits, if you want a labeled compounds, sealed sources, or even technology, radiographic camera, radiochemicals, dosimetry systems, all are supplied by BRIT. You can go to the website of the BRIT and see what are the products they are supplying. And for the larger products, medical products, sterilization, processing, vulcanization of rubber, and many other, electron beam processing for insulation of cables, all consultancy, calibration of radioisotopes, all the facilities, services are provided by BRIT in the country. So you can go to their website and see what are the things they do. So I'll stop here, and thank you very much for your attention. I hope you are getting a feel of what the radioisotopes can do and how we can produce them in our facilities. Thank you very much.